just single variable, ¿no? Ajá, entonces es easy. Okay, another approach is using a squeezy theorem. Squeezy theorem. Let me recall. Squeezy theorem. Suppose that we have three functions, f of x, and single variables, a calculus one. And you discover algebraically this relationship between the functions. So in other words, supposed to understand a little bit geometrically the idea. Suppose that we have three functions. And one point specific is a, wow, too much, too heavy. Okay. And this is f of a. One point in the plane. And we have one function, que is f, suppose. But we have another function, suppose g, something like that, and h, something like that. Entonces, I discover, suppose the red one is very, very, very complicated, very, very complicated, very, very complicated. I have no idea. Algebraic is complicated. Complicated. It's I, no? It's I. Complicated. It's very complicated. So this is very, very complicated. However, this is not complicated. Therefore, I apply the limit in g, I apply the limit in h. Si es the same value, entonces I infer que the limit in f is the same. Using the famous squeezy theorem. I suppose that everyone remember this idea. Now I take the expression here. The expression I can see, for example, the expression x squared divided by x squared plus y squared. So I take in the top, not 4, sino 2. It's obvious que it's in between 0 and 1. It's obvious, right? Because the numerator is smaller than the denominator. If you multiply the entire inequality by x squared here, x squared, x squared, x squared. So we have 0 less than or equal x to the 4th power over x squared plus y squared greater than or equal x squared, because x squared times 1 is x squared. And we have similar situation of this. Okay, so this is complicated. I know this is my original problem. However, I determine, for example, the limit of this case 0. And the limit of this is single variable, and the x approaches to 0 of the x squared is obviously 0, and this limit is 0, using a squeezy theorem. Very, very useful, a squeezy theorem, and multivariable. I bring another more interesting and complicated. Suppose this example is a limit and the x comma y approach to the point 2 comma negative 3 of the one complicated expression que is 2x minus 2 square over square root x minus 2 plus y plus 3. It's obvious that, well, the first thing you should do is plugging in the expression, and you get 0 over 0, no? It's obvious, no? 0 on the top, 0 on the bottom, is undetermined, or indeterminate. Now I try to do using a squeezy theorem. I take the expression, the complicated expression. Sorry, this is a square. Is x minus 2 square plus y plus 3 square. It's obvious that this expression is positive because it's a square and a square root is positive. You take no plus and minus, you take only the positive sign of the square root. So this is positive, so this is greater than or equal to 0. I make an approximation here. An approximation is I mentally mentally delete this part mentally. And when you delete that part, you obtain this expression as 2x minus 2 over square root x minus 2 squared. And this is true, of course true, because when you delete the y part and the denominator, I suppose that the denominator is smaller. So this denominator is smaller, the entire fraction is greater than. So this expression is greater than this. And I manipulate algebraically. This is 2x minus 2. And this is a square root square is x minus 2. But wait. This is sorry, this is a square, right? I forgot the square. And this is x minus 2 a square. And well, actual but if you want. But it's okay. And you delete this and this, cancel out. Now our expression is 2x minus 2. So now you apply the limit, single barrel. Limit when x approaches to 2. Okay, the x value at the beginning, look, 2. Of this expression is 2x minus 2. 2 minus 2 is 0. It's 0 here and 0 here. According to the squeezy theorem, the limit is 0. You understand this or not? Everything is clear or confusing? Squeezy is another approach to apply a limited multivariable. I promise in the review package for the test 2, we continue doing a little bit. Another approach, the last one, is rationalization. This is classical. This is similar to the calculus 1. Limited when the x, y approach to 2, 1 of the one expression that is x minus y minus 1 divided by square root x minus y minus 1. Okay, as always, you plug it in. X is 2, 2 minus 1. 2 minus 1, minus 1 is 0, no? It's 0. And here is 2 minus 1 is 1, square root 1 is 1, and 1 minus 1 is 0. 0 is 0. Again, is indeterminate. Okay, you plug it in. See, the answer is a number. Is the answer because I suppose in this case the function is continuous. So it's continuous. The limit and the function evaluated at the point is the same value. Therefore, you finish. But when you have problem in determination, undeterminate, indeterminate, is when you manipulate something. How you manipulate? Well, let me try rationalization. This is classical in algebra, elementary algebra. For example, you have this expression, and you multiply top and bottom by the conjugate of this. The conjugate is square root x minus y plus 1. Square root x minus y plus 1. This is working like a smart one can help me to rationalize. Rationalize means eliminate the radical in the denominator. This is classical. And okay, so when you multiply the top part, the bottom part first, is this time this is x minus y minus 1. Okay, this is classical, a minus b, a plus b. The answer is a squared minus b squared, no? A is radical, x minus y, and b is 1. Entonces subtraction, this subtraction is this subtraction, no? Okay, entonces in the top we have x minus y minus 1 times square root x minus y plus 1. Okay, nice. This is cancel out. This is the reason. This is a factor I need to eliminate, delete, to remove the indetermination. Entonces my limit look like that now. Let me see. It's a limit when the x comma y approaching to 2, 1 of this expression, because this is square root x minus y plus 1. I'm plugging. This is square root 2 minus 1 plus 1. 2 minus 1 is 1, 1 plus 1 is 2. That's the final answer. This is an okay. So basically, we studied 5 different ways to do the limit and multivariable. The first one is approach to different trajectory. So at least one failed, the limit do not exist. The second was the polar, convert to polar, take advantage the symmetry with respect to the origin. And finally, one exquisite theorem, rationalization. And when you see the face of the example, you make a decision what way you use. Okay, now I want to talking about the continuity. So this is the limit. Now continuity is in column 1, continuity. Continuity is in column 1. You have a function y equal f of x. And you prove somehow, okay, you want to be continuous in the specific point at x equal a if 3 conditions. Number 1, the limit exists. Yes, we can find L. Second, the function exists. The function evaluated in A exists. A and L is always equal the same number. And the 3 conditions, they are coincidence. So in other words, so you try to express a continuity in one expression as a limit and the function is the same. This is the big idea for the continuity. Okay, continuity. Now, in multivariable is the same. It's the same. Okay, we have, for example, one elementary example, we have a function in 3 dimensions, 2 independent variables, and 1 dependent variable is c. Entonces we define this like a piecewise function. Suppose cosine y sine x divided by x. And this is valid for xy point, not 0. And cosine y only for the point x comma y equal to 0, 0,0. Now you define, for example, one piecewise function formed by 2 pieces. When there's completely no origin, it's cosine y sine x divided by x. And when the origin is just cosine y. So I need to evaluate in 0, 0. Because in my opinion, the critical point, the point maybe we have some problem. It's obvious que cosine 0. And cosine 0 1. Now you apply the limit. And now the limit when the x comma y approaches to 0, 0 of this expression. It's obvious I take this expression because remember the limit is not exactly the same on the point. It's close to the point in any direction, but it's close to the point. So it's cosine y sine x divided by x. Okay, I try to do my best in this limit. Why not using the property for the limit? No, limit. You separate y no. You separate cosine y. In this case, x comma y approaches to 0, but this depending only the y. So y approaches to 0. Multiplication, limit when x approaches to 0 of sine x divided by x. Entonces cosine 0 es 1. That part is 1. That part is 1. Is the fundamental trigonometric limit, no? 1 times 1 is 1. They are perfect coincidence with the limit and the function evaluate. Now this function is continuous. In this case, continuous at all real numbers. So it's at R2. Because the only critical value que maybe is discontinuous 0, and I prove que es continuous. Entonces it's no big deal the continuity because, for example, when you have several functions, you have F and G together. So the combination, addition, or subtraction, si es continuous. Suppose que F and G are continuous. Multiplication is also continuous. Division is also continuous, except when the G is not zero. Any operation. The power is continuous. Root is continuous, except when the F is greater than or equal to 0. And the composition also is continuous. So the composition is supposed to F or composition G and X, Y is continuous. So the combination of the function, for example, polynomial, the classical polynomial, continuous, rational, inside the domain, rational, inside the domain, inside is domain, no? It's also continuous, no? Si it's outside, no, of course. Sine, cosine, trigonometry, pero no tangent, no secant, sine, cosine, and exponential. It's the classical example, you know very well, of the continuous function, and the combination and multivariable, no only x, like a cal 1, x and y together, is continuous. So suppose a couple of the examples illustrate this big idea. Look, suppose you have f of x equals sine x squared cosine y. Another example is f of x, y is exponential x squared plus y, square root y squared plus c squared, and this is 3 variables, c plus 3, divided by sine, wow, x times y times c plus 5. Let me erase that part to see much better. Okay, it's 3 variables, f, x, y, z. Entonces this function que I provide now is a combination polynomial, rational, trigonometric, sine, cosine, exponential. It's obvious que es the combination of the continuous function, and the answer is both are continuous. So you don't need to prove that. Only see, in 1 second you determine. Bueno. In this case we have division, but I know that this, I suppose que this expression is always positive because it's a square, no? And no problema with the radical. And denominator, no problema, because the sign is bounded between a -1 and +1. Plus 5 never is negative 5. Okay, so what is the maybe possibility is discontinuous when the denominator is 0, but the denominator never is 0 because plus 5 never, subtraction 1 is 4 and addition 1 is 6. So it's oscillated between -4 and +6. There's no problem, they are continuous. Any question, guys? Clear? Confusing? Continuity is no big deal. The limit is a little bit sophisticated, I understand. But okay, as always, I try in the test, no super complicated problem. There are super complicated problems that I cannot solve it. So this is crazy. However, we are doing the traditional. Okay, so the next step in this chapter is a partial derivative. Partial derivative. Okay, this is totally new. You never see before in your life. Partial derivative. Okay. So far, guys, everyone follow me? Come on. Clear, confused. Ricardo is clear. Ricardo, everything is clear for Ricardo. The idea for the limited and the idea for the, of course, we need more examples, no? Entonces, that is a reason I left the homework. Daniel González, Jocelyn Restrepo, Javier Hernández, Robin Soto, Heidi. Did you receive my email, Heidi? Heidi, Heidi, answer me. I don't know what happened with the Heidi microphone. Okay, okay, this is clear. I get going. Continue. Partial derivative, partial derivative, partial derivative. What is that? You know definition for the derivative in Cal 1. Okay, in Cal 1, derivative is, definition is limited when the h approaches to 0 of the f of x plus h minus f of x divided by h. This is the definition. See, this limit exists, the function is differentiable. But in multivariable, remember, we have several directions. So that is the reason that we use a partial derivative. Que es, in other words, the derivative are two standard fundamental directions. So we found, for example, the partial derivative in the direction x comma y at the point x comma y, and the definition is the limit, again, when the h approaches to 0, it's the same idea, of the x plus h comma y minus f of x comma y divided by h. And likewise, in the other direction, que es x comma y, is the limit when the h again, or another variable, approaches to 0 of the f in x comma y plus h minus f of x comma y divided by h. Let me try to interpret this new idea. So you consider, for example, in the first one. Okay, this is the new notation for the partial derivative. Okay, you need to be super familiar, guys, from now. Notation is, you see f subscript x. This is a partial derivative of the function with respect x. What mean with respect x? Que yo considere que x es a variable, pero y no. Y is a constant. Okay, let me see the interpretation, the geometry interpretation of this idea. This is one notation. Another notation is a little bit weird. It's something like that. This is delta f over delta x. It's a partial derivative with respect to x. Partial derivative of the function f with respect x. And another notation is capital D x f. Okay, in my opinion, the most popular is this, and the second in popularity is this. Okay, this is used seldom. Okay, entonces es the same idea, is compute somehow the rate of change of the one function in one specific direction. You see, bueno, professor, entonces, in another direction, well, no, relax. This is partial derivative. Entonces, the word partial suggests me que the idea is incomplete because we have multiple directions. No problem. Maybe not today. We study direction in any direction, but this is partial today. Okay, but I would like to show you the interpretation of this. Let me try to do my best. I go to GeoGebra now to illustrate the interpretation of the partial derivative with respect to x and partial derivative with respect to y. Okay, look at that. Boom. Do you see GeoGebra? Do you see GeoGebra? And we have here, to illustrate this idea, we have a function, paraboloid. Do you see GeoGebra? Yes or no? Yes, Ricardo. Okay. Guy, are you connecting or no? Daniel, are you there? Ricardo, what happened to microphone? Okay. Okay, this is the whiteboard, and this is GeoGebra. Do you see GeoGebra, right? Or no? Yes or no? Answer me with the chat. Come on, come on, come on. What's going on? Here, Professor. Okay, Annette. Okay, good, Annette. Come on, I need feedback, guy. Communication. Brandon, Heidi. Heidi, are you there or no? You're absent. Heidi. Robin, are you there? Javier. Okay. Okay, entonces, I suppose que you see GeoGebra, right? Okay, look at that. I plot the point on the surface. Here, over there. Bam. This point is A. Let me make a zoom. It's a point A on the surface. Now, I do the graph, for example, x equal constant. It's a plane. This plane is parallel to the y-axis. Look, I remember y-axis is the green one. And the intersection between the surface and the plane is this curve. Okay. Now I plot. Let me see if this or no. Oh no, it's the other one. Okay. And now you plot. Okay, the tangent line. Look, the tangent line. Let me remove the paraboloid. Let me remove the plane. Okay. Entonces, in that moment, we have a problem of the calculus 1. Okay, and in the y direction, when the x is constant, I suppose que es x constant. Let me try to change this. Okay, you change the y bar value, and you see that the derivative is the slope of the tangent line, exactly like a calculus 1. But in the direction, in this case, was the direction of, let me see, of y, no? The direction of y, que es the green. Okay, likewise, similar, the same idea. We have paraboloid again. But let me delete this, and delete y, no, this. Okay, suppose now we have y equal constant, it's a plane, our famous paraboloid, and the intersection is this, I suppose. Yes, the intersection is this. This is geometric interpretation of the partial derivative. Now the curve, I suppose it's this. In blue color. So you remove, for example, the paraboloid, you remove the plane, we have only the curve and the tangent line, and you manipulate this. Look, no, sorry, it's this slider, you manipulate this. Okay, it's the same idea, but in this case, partial derivative, when you're talking about partial derivative, is in the x direction or in the y direction. The question can fly in the air. Oh, professor, what's going on in the other direction? No. We study everything, I promise. Okay, so what is the idea? What is the algebraic idea for the partial derivative? Let's do an elementary problem. I want to complicate a little bit. And so our goal so far is focusing in the computation, the partial derivative algebraically. Okay, it's similar, very similar to the calculus, but the consideration is that you consider it, for example, you have that function, easy, polynomial, plus 2 x squared y cubed minus 2y squared. I want to compute partial derivative with respect to x. Okay, what is the idea? Well, the idea is that you consider that x is a variable, and y not. Why you treat like a number, like a constant? So when you differentiate this, it's 3x squared, easy, plus something, and you differentiate that part, is 2x, but y cubed stay the same because you consider it like one number. Do you understand this? It look like weird, but this is the idea. And the derivative, the last part, is depending only the y, derivative with respect to x is 0. End the story. I differentiate. This is partial derivative of the function with respect to x. Different notation we can use. And now with respect to y. With respect to y. Partial derivative with respect to y. Well, so you differentiate the y part. Derivative, the first part is 0. Derivative, this is 3 x squared y squared. It doesn't matter the order. Minus derivative, the last part is 4y. And this is partial derivative f with respect to y. Do you understand this or no? Some students confused, very confused in that part. Okay, let's see another example. This is elementary example. I promise I want to complicate a lot of this. Okay, you consider that the other variable that you don't differentiate is a constant, it's a number. Okay, suppose another example easier. F x comma y is equal x cubed plus x squared y cubed minus 2y squared. Okay, let's do it again. Partial derivative with respect to x. Bueno, es 3x squared, ¿no? Plus, with respect to x, 2x y cubed. And derivative with respect to x is 0. Okay, now partial derivative with respect to y is 0, the first part, because depending only the x, entonces 3x squared y squared. You using the power rule, no? I suppose you remember the power rule, no? Minus 4y. It's okay? Let's, by curiosity, and using the new notation, no? Suppose I want to find the second derivative. The notation is like that, second derivative. So you differentiate first with respect to x, and secondly with respect to x again. This is one possibility to express the notation. Another possibility is delta 2f with respect x squared. This is another notation. Remember, in calculus we have the Newton notation, we have the Leibniz notation, and you use it in either way. This is more clear, more easier, in my opinion. However, you lost information in the Newton notation. Okay, so you differentiate again one more time with respect to x. So you take that, I did the derivative with respect to x, and you differentiate again with respect to x. Entonces es 6x plus something plus 2y cubed. Everyone follow me, guys? Or you are totally lost? Okay, you take the derivative with respect to x. I did the first time, one derivative, and you differentiate again this expression with respect to x. Entonces you focus en x, y is a constant, entonces stay the same. And now suppose y. So que second derivative of the x with respect to y 2 times. Entonces es, you take this expression and you differentiate with respect to y is 6 x squared y minus 4. Wow, because derivative y with respect to y is 1. 4. This is the second derivative. Super easy. However, bueno, professor, I can compute, for example, the second derivative, differentiate, for example, x first and y second. Yes, we can. The notation is partial second derivative with respect to x first and with respect to y secondly. Okay, this is the advantage of this notation. Can you see the order? Well, in this case, you see order x first, y second. It's okay. Either way. Entonces you take, for example, the derivative, this derivative again, but you differentiate now with respect to y, and this is 0, and this is 6xy squared. Okay, because these 3 fly outside, is 6 and decreasing minus 1. I suppose, guys, you remember very well the power rule, no? We practice a lot of time in Cal 1 and Cal 2. Suppose you differentiate in different order, like that. This is second derivative with respect to y first and x secondly. Okay, this is delta x. Entonces, you differentiate, pero you differentiate this expression with respect to x now. Entonces es 6xy squared, and the derivative, this will respect the x is 0. Wow, fantastic. And you prove somehow, okay, this derivative, it doesn't matter the order, the second derivative is the same. Keep in mind, second derivative xy always is equal second derivative yx. This is a theorem. Clear out theorem. It's a theorem. Do you understand this or no? Of course, you need more practice. Partial derivative, partial derivative, partial derivative. What's the key idea for the partial derivative? The key idea for the partial derivative is you differentiate with respect to x. You consider y constant. So you differentiate with respect to y. The x is constant. But let me see another example. Another easy, and you help me. Come on, I need help. I need help. This is super easy. I select for you. Suppose we have that function. F of x, comma y is equal x squared, y squared. I need everything. Partial derivative with respect to x, partial derivative with respect to y, partial derivative x, partial derivative xy. By the way, confirmation yx. Come on, who help me with the first? Number 1, 2, 3, 4, and 5. Partial derivative with respect. Who help me? Come on, using the chat to answer me. Follow me. Okay, follow. Pero no, I need participation. Come on, Gerardo. Compute the first derivative, the partial derivative with respect to x first. Come on. Easy problem. Okay, it's available for everyone. It's clear for everyone. They have a common sense about Cal 1. The only consideration is when you differentiate with respect to x, you consider y as a constant. You treat like a number. Come on, participation. Nobody won't participate.
Professor,
go ahead.
I think a lot of our messages are not going.
You don't see the whiteboard?
I see the whiteboard, but I'm typing messages and it looks like it's not going through.
I understand. Yeah. Okay. Pero speak, for example, what is the expression for the partial derivative with respect to x? Is 2 times something. Come on, speak.
2xy squared.
2xy squared. Very well. Okay, because you differentiate only the x part and the y squared stays the same because it's considered constant. What about the partial derivative with respect to y? Come on, another participation. Come on, Ricardo, Restrepo, Annette. Can you prove me that you are advanced student in the test 1? Okay, 2x squared y. Exactly, Restrepo. Restrepo say 2x squared y. Very well, Restrepo. And second derivative, we respect x 2 times. 2, x first and x secondly. When you differentiate this expression with respect to x, what's the answer? In this moment, I don't see very well the chat. Well, okay, let me try it by myself. This is 2y squared, making sense, right? The derivative x with respect to x is 1. And you consider the y squared is a constant. Second derivative with respect to the y 2 times. Well, I forgot one derivative. It's fyy. Sorry. This is 2x squared, right? And the partial derivative xy is 4xy, no? And this is exactly the same. Because when you differentiate, for example, this with respect the y, is 4xy, decreasing one. The idea is clear or the idea is confusing? The idea is clear or the idea is confusing? Come on, I need to hear opinions. This is Chinese or Japanese? Everything is clear? Daniela, Leonardo, Aguilar, ¿es clear or es confusing the idea? No? No opinion? Okay. 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 Entonces, I assume that you have some idea how we compute easy partial derivative. Now let's study the chain rule. The chain rule in multivariable. The chain rule in multivariable. Suppose we have one function that depending of two variables, but x depending of the another variable, que es t, and y depending of another variable, que es t. Okay, entonces, how you find the derivative of c with respect to t? This is the goal. So we have a function that depends on two variables, maybe two, maybe three, and each intermediate variable, x and y, depending of another independent variable que es t. Okay, so I propose you to set out the formula for the partial derivative. In this case, no partial, it's the ordinary derivative. Look, it's important. Are you familiar with this notation, no? dy dx. This is ordinary derivative. Now, partial derivative y with respect to x is a new notation, or f of f in x. This is the same, no? In this case, f. Okay, entonces, to visualize the formula is you control the tree diagram. And tree diagram is z dependent to variable, x and y, and x dependent to t, and y dependent to t. This is the tree diagram. What is the formula? The formula is dz to t is equal partial derivative z with respect to x, que es this segment, time ordinary derivative x with respect to t. What is the reason that this is delta and this is just d? Because in that part we have several variables to say it's partial derivative. In this case, no. In this case, calculus 1, x dependent on t. This is ordinary derivative. I finish no. Because see in this segment that we did that part and that part. And so now I finish this part and this part is partial derivative z with respect to y time dy dt. This is the formula for the chain rule in this problem. Let's see example. Super easy. No big deal. This part is totally algebraically. No big deal. Suppose that we have function z que is equal x squared y plus 3 xy4. However, semicolon, x is equal sine to t, and y is equal cosine to t. I need to compute dc dt. Bam. Okay, let's do it step by step. Okay, in the formula we have 1, 2, 3, and 4 elements. Let's do it separately. Finally, we integration everything. Suppose partial derivative z with respect to x is equal. You take this expression and you differentiate with respect to x. This is 2x y plus with respect x is 3 y to the 4th power. I did that part. Okay, now partial derivative c with respect to y. I try to do that part. Is, well, with respect to y is variable, x squared no, entonces x squared plus, well, with respect to y, this is 4, this is 12, xy cubic, because decreasing this polynomial. Okay, I did that part. Now, I try to compute dx dt. This is cal 1. S2 cosine 2t. Chain rule, the classical chain rule. And dy dt. Derivative cosine is minus sine. Okay, now finally you put together in the formula. Okay, this is too heavy algebra. It's okay, this is easy. You copy this expression, que es this. However, I suppose that my final answer is expressed using the only one independent variable, que es time, es t. Entonces, look, I want to copy, pero super quickly. This is 2 times x. Pero who is x? Es sine 2t. Time y, que es cosine t. Plus 3 times cosine to the 4th power of t. ¿No? Okay, cosine 4th power t. Multiplication, everything multiplication by this, que es 2 times cosine 2t. Of course, we can FOIL, multiply the coefficients. I don't want to do that because it's the elementary algebra. Plus something. This is x is sine square 2t. Plus 12, x is sine 2t. Y is cosine cubic t. Multiplication, everything by dy dt, and dy dt is minus sine. Okay, I don't know why I put here z. It's not c, it's c prime, or dz. Okay, do you understand the idea or no? It's no big deal, it's relatively easy to understand. Okay, I bring 2 more examples in which I complicate a little bit more, because sometimes we have every possibility. We have a lot of combination in this case. Suppose another chain rule in which I have the function c that depending xy. Okay, good. However, x depending of 2 variables, okay, called s and t, and y depending of the another function is h, x and t. Okay, we have one big function in which we have the dependent variable is c, 2 intermediate variables x and y, and x and y depending also 2 functions of the 2 independent variables is s and t. So this is a case in which you have 2 independent variables, not only one t. So what is the tree diagram? The tree diagram I see depending of x and y, and it's depending on s and t, and this depending on s and t. So suppose I want to find the partial derivative z with respect to s. Okay, so you cover any trajectory que relate with the s, que es this and this, and also this and this. And the formula is partial derivative z with respect to the x times partial derivative x with respect to s. In this case, partial. Why? Because x dependent 2 variables, not 1 variable. So are you using the d when you have, for example, x depending of only 1 variable? So depending of 2, the partial. Plus partial de z with respect to y, que da branch, time partial de y with respect to s. Okay, easy. Now let's do in partial derivative z with respect to t. In this case is in this direction, y in this direction. Entonces partial de z with respect to x time partial de x with respect to time t. This is delta t plus partial derivative z with respect to y and partial derivative y with respect to t. Okay, this is the formulas. Let's do an example. Easy example, no big deal. To understand, this is the case in which we have two independent variables. Suppose example que es z equal exponential x sine y. And we have x equal xt squared. And we have y is equal x squared t. Semicolon, semicolon. This is the function. And you need to find partial de z with respect to this. And why no partial de z with respect to t. Okay, it's our independent variable. Okay, so let's compute the component by component. Suppose I focus in the first equation, this one. Okay, so I need partial de z with respect to x. Is, you know, in the function que state the relationship between z and xy, I differentiate the exponential, no? And the derivative of the exponential is the same exponential, but you suppose that the part depending only the y is a constant, and you copy exactly the same, copy. It's like you suppose c equal in column 1, 2e to the x. How you differentiate that? Is 2 is a constant, I just copy and paste, bring down, and derivative e to the x is the same function. It's clear. Partial de z with respect, clear, super, we see that, wow, Annette. With respect to y, entonces derivative sine cosine, entonces exponential is a constant, in this case, yeah, clear, Carlos. Cosine y. Cosine y because derivative sine cosine. Okay, I did that part. Boom. Yeah, I did that part. Boom. Now I need to find partial derivative x with respect to s and partial derivative y with respect to s. Because I tried to compute that part. No? So the partial derivative x with respect to s is, you know. So you differentiate this with respect to s. You consider que t squared is a constant, entonces derivative s with respect to s is 1, entonces the answer is t squared, just t squared. And partial derivative this with respect to s is 2st. I have that put together. Entonces be careful, because in the final answer, I want to skip that part, of course, because this is stupid algebra. You, in the final answer, you express it only using the independent variable, que es s and t. So you replace x for xt squared and y for x squared t. This is elementary. Let's do it now. Partial derivative y with respect to s and partial derivative y with respect to t. No, I did that, but I forgot something, no? Partial derivative, this is this. Entonces, partial with respect to t, coño. This is t now. Partial derivative with respect to t. The partial derivative y with respect to t is x squared. It's obvious, right? And partial derivative, wait, this is partial derivative y with respect to s, I did that. Partial derivative x, entonces this is partial derivative with respect to x, I did that. I forgot partial derivative x with respect to t, no? Okay, look here. Partial derivative of the x with respect to t is easier, is 2 st. Done. Done. The rest is just substitution and the corresponding formula and end the story. Okay, my question is, do you need another example of this or no? This is elementary, right? Let's move on to another more interesting, no? Wait, no? Another interesting thing. No? It's okay? You understand the idea? Of course, you need practice. This is clear for me. But the practice, you are doing the homework. Remember, you are doing the homework. It's perfectly possible. Okay, one question of the homework, you send me, I solve for you because you don't understand very well. I tried. This is my way to understand how you study this class. Okay, let me try now to explain the formula to compute the implicit differentiation. Implicit, because the formula differentiation. Okay, the formula that we see before, I suppose it's explicit. Remember what is the idea implicit, explicit in mathematics? Implicit is when the dependent variable is not isolated. Let me put one elementary example of the calculus 1. If I want to prove derivative for this elementary example of the cal 1, we apply the formula to compute the implicit differentiation in multivariable. Okay, suppose in cal 1 we have this problem. Okay, in cal 1 only we have two variables. We have y and x. I need to compute dy dx. This is a cal 1 problem. But this case is implicit differentiation because y is not isolated, and maybe isolated y is a little bit complicated or impossible. Sometimes it's impossible. Okay. Therefore, you differentiation on left hand side, differentiation right hand side. Okay, by the way, differentiation right hand side extended is 0, no? Derivative. And you're using this product rule. And product rule of differentiation, the first function is 2x. 2xy. I copy product rule plus differentiation. The second part is x squared. So you put y prime, or some professor, I don't know, do you like that way? I like that way. Another professor explain like that. dy dx. I don't know if you using this notation. Remember, y prime is equivalent to dy dx, no? It's no secret, at least for me. Because I prefer y prime. I don't know why. Suppose the teacher explained me this using y prime. So I create this habit. But I need the easy part. Plus the derivative of the second part is this. Is 6y prime. Because remember, y is the dependent variable and the treatment is different, dy dx and dx dx. I suppose que es 1, no? That is a reason. Because the chain rule, the tree diagram is x depending on y. This is basic tree diagram. And derivative this with respect to x is 5, and this is 0. Okay, so what should I do? Well, isolate the y prime. Easy. I move everything to the left. So we have x squared y prime plus 6y prime is equal minus 5 minus 2xy. I move this. I factor out y prime. X squared plus 6y equal negative 5 minus 2xy. Finally, y prime is negative 5 minus 2xy divided by x squared plus 6y. This cal 1. I finish. End the story. However, let me show you something magic. something magic. Suppose I define capital X. Capital X is the same f of x. But in this case, I suppose it's x comma y. And I suppose the right hand side is 0. So it's the same problem, but I manipulate a little bit the expression. I'm going to put every variable to the left. Okay, basically is x squared y plus 3y squared plus 5 x minus 10 equals 0. Okay. Yeah, I computed, why not, the famous partial derivative of this function with respect to x. So now, multivariable, partial derivative, new thing. Now, partial derivative is, okay, you differentiate this, but you consider partial derivative. In this case, no. In this case, you consider the connection in between y and x. No, partial derivative. Partial derivative is, derivative this is 2xy. Derivative this with respect to x is 0. Derivative this is 5. Okay, I finished that. Partial derivative now with respect to y is, when you differentiate with respect to y, this is x squared. When you differentiate this with respect to y, is 6y. This is 0, this is 0. And it's no coincidence that this expression is exactly the same, this expression with the opposite sign. And this expression is exactly the same with this expression with the same sign. So what is the formula? The formula is dy dx is equal minus f, capital F, okay, is the implicit when you move everything to the left and you put the right hand side 0. This new function differentiate partial derivative with respect to x and partial derivative with respect to the y. This is the formula, and that formula we using in more complicated. For example, see, I need to find partial derivative with respect to z, partial derivative of c with respect to x. The formula is minus partial derivative with respect to x divided by f partial derivative with respect to z. Likewise, partial derivative z with respect to y is minus partial derivative with respect to y divided by partial derivative with respect to z. This is the formula for the implicit differentiation. Let's see example. Elementary example. No big deal. After I complicate, but no now. Okay, let me try to find one good. I like that too much. Look, implicit differentiation. No chain rule, you know, implicit differentiation. Suppose this example. Suppose x e to the y plus y e to the x minus 2x squared y equals 0. They need to find dy dx, like a Cal 1, but using the tool of Cal 3. Okay. And then is, bueno, the formula says que es minus partial derivative with respect to x divided by partial derivative with respect to y. And partial derivative with respect to x is, differentiation this with respect to x is e to the y. Differentiate this with respect to x is, stay the same, you know? And differentiate this with respect to x is minus 4 xy. Good. Partial derivative with respect to y. Okay, differentiation this, stay the same. Plus, differentiation this with respect to y. Y is a constant. Derivative 1 is e to the x. Differentiation this with respect to y is minus 2x squared. Finally, you put the minus here. Oh, I prefer not put the minus in the front. You know, you change the sign of the top part or the bottom part. It doesn't matter. You change the sign. Okay. Anyway, I put it in my paper like that. Minus. I just copy in the top this expression. e to the y plus y e to the y minus 4xy divided by this expression, x e to the y plus e to the x minus 2x squared. Done. Super easy. Super easy. Let's do it more complicated. More complicated using 3 variables. Implicit differentiation, guys. Implicit. We are talking about implicit differentiation. Whoa. Okay. After this class, I suppose that you are strong doing the differentiation and multivariable, because next class we are using this. Okay. Suppose this example is 3x squared y minus yc squared minus 4xc minus 7 equal to 0. Okay, nice. Okay, you suppose que that function is capital F. Capital F and implicit. Dependent x, dependent y, dependent z. They need to find partial derivative with respect to the x, partial derivative z with respect to y, and y no, partial derivative c with respect to no, partial derivative y. Why not? I change a little bit. Wait a second. Partial derivative of y with respect to x. Okay, the formula is clear. The formula is minus fx divided by fz. The formula here is minus fy divided by fc. And the formula here is minus fx divided by fy. And let's compute it separately. Fx, fy, and fc. And they are combination. Okay, well. F and x is, differentiate this, is 6xy. This non-dependent of c, 0. And this, yes, dependent of c is 4 dependent of x, sorry, entonces es 4c, minus 4c. Everyone follow me? This expression, I copy here. Yeah, I copy here. F and y is, well, differentiate with respect to y now, is 3x squared minus c squared. And this don't depend on the y is 0. And this is constant is 0. This expression I copy here, and here. Okay, and if you want, do some algebra, but this is not important. Now, the last one is differentiation with respect to z. Well, to say this is do not depend on c. Yes, this is depending on c. So says minus 2 yz. And this is depending on c. Derivative c1 is minus 4x. And this expression I copy here. Super easy, super fast. No problem. Okay, let's practice a little bit. Higher order derivative. So, okay. Let me try to summarize. We define today partial derivative. Is the derivative, but derivative in one direction, in the x direction or in the y direction, no in another direction. Entonces, in practice, you find the derivative under the consideration that another variable is constant. When you differentiate with respect to x, y is constant. We studied the possibility of the chain rule when you have several functions and you are doing the tree diagram to determine specifically the formula for our example. And after that, using that. And finally, the implicit differentiation is using the implicit differentiation formula, is amazing. Let me try one to summarize everything. One problem. Suppose that problem in which you have exponential xy plus z cosine x. Okay, so little by little, we compute the partial derivative using that notation. Why not? Okay, we respect the x. Guys, look, this letter and this letter is similar in the Greek alphabet. This is delta. This is capital delta, and this is a lowercase delta. And this is the notation, no? Okay, using for define a linear notation. Okay, you know, okay, this is equivalent to say f of x using this another notation. Okay, so this is partial derivative with respect to the y. So you consider que with respect to x, sorry, que x is the only variable that exists, and the rest no, the rest is a constant. Okay, so when you differentiate this, exponential is the same exponential, okay, and you differentiate the argument, que es with respect to x and y. Entonces the answer is y e to the xy plus or minus, I don't have idea. I suppose it's minus because the derivative cosine is sine, and c is considered a constant, sine x. Good, very good. Now let's do in partial with respect to y. Well. Okay, it's similar because in that part we have y, but in this part we have no y. Entonces the derivative of that part is 0. Entonces es x e to the xy. Super. Okay, let's complicate your life using second derivative. So we compute the derivative x and x again. So you differentiate the first time with respect to x. I did that. It was this expression. Now all over this expression, I differentiate again with respect to x. Entonces this situation happens similar. Exponential is the same function, but when you differentiate the argument with respect to x, one y extra fly outside. Entonces y squared e to the xy. Everyone follow me, guys? Minus, I don't know if it's minus or plus. Well, it's sine is cosine, entonces c cosine. This is the second derivative. When you differentiate 2 times with respect to x. Okay. Now suppose I want to be continued this idea. You differentiate with respect to y now. So I did the derivative with respect to x is this expression. Now over this expression, I differentiate now with respect to the y. Well, so when you differentiate with respect to y, usually you consider it, okay, you consider it, look, like a product rule, no? Because this depends on the y and this depends on the y also, no? And the derivative, the first part is 1 with respect to y. Multiplication by the second function is xy. Plus something, plus something, plus something, plus something, plus what? Plus y. This y stays the same. And you differentiate this with respect to y. So it's like x e to the xy, no? Because when you differentiate e to the 2x in calculus 1, it's e to the 2x times 2, no? Because derivative the other part with respect to x and y. And this is the extra y que go outside. And the second part do not depend on y, entonces es 0. Okay. Let's do it now. The partial derivative with respect to y. Okay, entonces I take this expression now. Okay, I differentiate with respect to y. It's easy because no product rule. No, because x is considered a constant, no? And differentiation this with respect to y. we have one x extra that go outside like a factor into the x1, something like that. And now, why not, by curiosity, let's do the partial derivative with respect the y first, x secondly. Okay, get this expression now, and you differentiate with respect the y, with respect the x, sorry. Okay, I did the first y, get this. Now I need to do the second get x. Entonces we just apply the blood rule. It's obvious, right? Derivative is with respect to x1, multiplication by e to the xy, plus something. Derivative, the exponential, is the same exponential. And doing the differentiation with respect to the x, and when you differentiate with respect to the x, y is considered constant, so we have one y here, and don't forget this x extra. You compare this expression, and this expression is exactly the same. So the order of differentiation is not important. Okay. Suppose I want to compute the derivative of the function in that order first. Okay, with respect the c. Okay, I forgot. With respect the c is okay. We come back to the beginning to reach an expression, ¿no? Entonces es obvio que es non-dependent c exponential, and this is c cosine x, ¿no? Entonces derivative of c with respect to c es 1, entonces just cosine x. And the derivative, the second derivative, cz, differentiate this expression with respect to the z, pero do not depend c is 0. Suppose now the combination differentiate first with respect to the x and after with respect to the z. So we're using this expression again because I did the derivative with respect to the x first. Now I need to differentiate with respect to the z. It's obvious that that part is 0 and that part is a negative sign x. Make sense? Wow. Now suppose that you differentiate in that order y and c. Y and c is, let me see. Y first, get this. And I differentiate this with respect to c. No, we have no c, it's 0. That's it. Yeah. One more combination. That's it. Do you understand this or no? Super confusing? You need to organize your brain, no? To understand the partial derivative, right? But it's easy, it's relatively easy. Okay, guys. Now I want to spend the rest of the time that we have to explain one new part. Okay, any questions so far? Anyone follow me? Confusing? Come on. Participation. Heidi, Bahor. Do you hear me or no? Jocelyn?
Yeah, Professor.
Heidi, you hear me, right?
Yeah, I tried putting it in chat, but I don't think it's going through.
Do you receive my email, no? With explanation, right?
Yeah, I was gonna respond today. Everything was fixed, no worries.
Okay, super. Well, about the topic we are discussing, partial derivative. Do you understand or it's totally confusing? Come on, opinion. No opinion. Totally lost. Okay, entonces now I want to discussing a new thing, no big deal, super easy, que is the tangent plane. Okay. tangent plane. Okay, tangent plane of the one surface. Let me recall, Cal 1. Recall, in Cal 1 we have no plane, we have a curve, suppose. We have the function, y equal f of x, y. Entonces one specific point, A, this is f of A, we can apply linear approximation. This line represents linear approximation. And the formula for the linear approximation is the function plus the derivative evaluated at the point x minus a. This is a linear approximation. A linear approximation, bueno, near to the point, you know, que linear approximation and the function is approximately the same. So linear approximation is approximately f of x and the point close to the specific point in which you compute the linear approximation. So now in the 3 dimension we are doing exactly the same. We have surface, surface, like that. Okay, surface. So in one specific point, I want to put here, I need to find linear approximation. But in this case, the linear approximation is no line, it's a plane. Make a sense in which, okay, it's a plane, and the plane linear approximation x comma y, because it's 2 variable, is equal. Okay, so suppose that we have the function in 3 variable. Suppose z is equal f x comma y, sorry, x comma y. Yeah, you need to find linear approximation, que es the tangent plane, is in 3 dimensions, at the point a comma b. Okay, this point is bam, here, a comma b. A represents the component in the x-axis, a, and b is the component in the y-axis. And of course, the component in the z-axis is f and a comma b. Look, it's similar to this formula. This is the beauty of the mathematics. It's very, very similar to this, except that we have the function evaluating a comma b plus, in this case, we have 2 derivatives in the x direction and in the y direction, and determine 2 vectors, and the cross product in between this vector give me a normal vector. And the normal vector is the normal vector that I use to define the plane. I don't want to prove in detail this because it's very straightforward. Look in the equation. Look, you have the partial derivative of the function with respect to x, evaluating the point a comma b, and you have x minus a, plus partial derivative with respect to y, evaluating the point a b, y minus b. End the story. This is the plane that represents linear approximation in 3D. Let's do one example, and that's it for today. One more example, and that's it. Suppose the paraboloid. Suppose the paraboloid f of x comma y equal 9 minus x squared minus y squared. They need to find the linear approximation at the point 1, 0. This is a and b. And the c value is easy. Plugging in 1 and 0 into the formula, no? 1 squared minus 0 squared, 1 square of 1, into the 9 minus 1 is 8. But the famous point is 8. Linear approximation, or tangent plane, is a synonym, is this guy. This guy is 8 in our specific example, plus. Okay. So I need to compute the partial derivative. Okay, so in one corner of the piece of paper, I find the partial derivative with respect to x of the function, no? Okay, look, I differentiate these with respect to x. Bueno, es obvio que es minus 2x. And why not you evaluate at the point a comma b, okay, in our specific example is 1, 0. So x is 1, y is 0. The partial derivative do not depend on y. In this example, in other example, of course, yes. S minus 2. S minus 2. S minus 2. So I have this guy is a, this guy is minus 2. This parenthesis x minus a, que a is 1. There you go. A is 1. And partial derivative with respect to y is differentiate s minus 2y. Evaluate at the point que is 1, 0. Es 0 because y is 0, entonces es 0. Okay. Entonces that part disappear. Es 0 times something, ¿no? Entonces es actually es no plus, es minus. Es minus 2 times, que is this number, x minus 1 plus 0 times y minus 0. Oh, everything is 0 in the y. Look. Okay. Entonces, the answer is linear approximation is C is equal, remember I approximate the function a minus 2x minus 2, no? No, plus 2. Negative positive. The function, the plane is C equal 8, not 10, because a plus 2 is 10. 10 minus 2x. Final answer, this is the plane, que represent the linear approximation of this specific at the point. Okay. And curiosity. Well, that is over. It's almost over. Curiosity. We practice more example of this in the next class. You find the tangent plane because we have a normal vector. No? Okay, by the way, the normal vector is, in this case, the normal vector is the vector minus 2, 0, and negative 1. Okay, how do you find that? Well, after, in the next class, I explain the idea for the normal vector. It's confused. Okay, guys, remember the most important is today was the last day. Okay, the due date for send to me the test, written text or test on paper by email, and submit the homeworks. Remember, the homework is not mandatory, but it's extra point, and the test number 1 online. Okay, this is clear or is confusing? Today at midnight, tomorrow in the morning, I will see the work, I grade everything, I post it in Blackboard, and end the story. Okay, any issue, any problem, you communicate with me. I try to find solutions. Okay, solution, but individual, no here. In the lecture, we always talking about mathematics. The problem with the student, we discuss it in private by email.